My name is Sneha and I'm here with my teammates Vineet and Shivam to present this project. We would like to thank Dr. Kriti Srivastava for guiding us throughout this project. Imagine this, you own an electric vehicle and you wish to charge it for 10 hours overnight. If you use grid electricity, you pay 8 rupees per kilowatt hour, amounting to 80 rupees for just 10 kilowatt hours. But if you switch to solar energy, this cost drastically drops down to 3 rupees per kilowatt hour. Over time, you save thousands of rupees annually while also reducing your carbon footprint. This is the essence of a project, solar energy prediction and electric vehicle charging cost evaluation system. Global is transitioning towards renewable energy and electric vehicles. Solar is considered as a clean energy source as it does not produce greenhouse gases during its generation of electricity. Solar power EV charging reduces carbon footprint and energy costs. EV adoption is projected to reach 230 million vehicles by 2030. Solar energy is expected to account for 22% of global electricity by 2050.
So, coming to gaps in existing work, as we move towards smarter energy systems and increased electric vehicles adoption, accurate forecasting becomes more critical than ever. To achieve this, we need hybrid models that combine real time data with historical trends. Real time input helps us to respond quickly to sudden changes, while historical data ensures long term stability and reliability. However, when it comes to electric vehicles, we face added complexity. Challenges like unpredictable charging demand, station placement, and range anxiety can't be addressed by traditional models alone. We need forecasting models that intelligently integrate both mobility patterns and grid data to make EV infrastructure more efficient and user friendly. But building such models isn't possible without the right data. A major hurdle today is a lack of diverse and standardized datasets. Most available data is region specific, making it hard to create models that work globally. Establishing shared, diverse datasets is crucial for scalability and better benchmarking. Finally, even the most accurate model is useless if it can't function in the real world. That's why our model must be lightweight, scalable, and robust, designed to work under constraints like limited processing power and intermittent data access. Only then can we ensure practical deployment in dynamic and real time environments. Coming to the problem definition, with the rapid development of EVs in India and across the globe, there is growing pressure on charging infrastructure to be both efficient and sustainable. Solar energy, being a clean and renewable source, is crucial for reducing reliance on fossil fuels and lowering charging costs. However, users often lack the tools to optimize charging with solar power. Our solution addresses this by offering a real time dashboard that predicts charging cost and solar availability, helping users make smarter, greener charging decisions. So, the objective of the project lies in our project focuses on making electric vehicle charging smarter and more sustainable by integrating solar energy data with real-time EV usage. The first major challenge is gathering and integrating data from diverse sources, including real-time solar energy generation, weather patterns, and EV charging behavior. With this integrated data, we aim to predict solar energy generation in real time. By doing so, we can plan better energy usage and ensure that charging happens when solar power is at its peak, reducing reliance on the grid. Using this prediction, we then estimate potential cost savings, answering a key question: how can we lower EV charging cost by leveraging solar energy at the right time? Next, we analyze the energy needs of EVs by monitoring real-time charging patterns and matching them with forecasted solar power. This helps in deciding optimal charging windows, reducing both cost and environmental impact. Finally, all these insights are presented through a user-friendly dashboard that offers clear visuals, smart recommendations, and actionable suggestions, making it easy for users to make informed energy decisions. Dataset details. To forecast solar power output, we use a dataset with 4,214 samples and 21 features capturing key meteorological variables over time. This dataset includes crucial inputs such as weather data, which has temperature, humidity, precipitation, and many other factors and parameters measured at various altitudes. It also records sun angles like incidence, zenith, and azimuth, which are important for determining how much sunlight hits the solar panels. Our target variable is the actual power generated in kilowatts. Using this rich historical data, we trained our predictive models to learn the complex relationships between environmental conditions and solar energy output. This helps build a reliable foundation for forecasting. This slide explains how the real-time data can be fetched for the solar energy prediction and which is integrated with the dashboard which will be further shown. To make our system dynamic and responsive, we integrated real-time data using the Open Meteor API. This allows us to make live solar energy predictions based on current conditions. The API requires inputs such as latitude, longitude, and a timestamp, which together identify the exact location and time for which we want data. The API responds with the key features found in a historical dataset, which are temperature, humidity, cloud cover, solar radiation, wind data, and sun angles, keeping our prediction model consistent across both historical and real-time inputs. This enables us to bridge the gap between past trends and present conditions, allowing accurate, location-specific, and real-time forecasting of solar power generation.
So this is a proposed methodology where we integrate data processing, machine learning, and optimization to create the efficient solar energy prediction system. We start with the data source, which is a collection of historical solar energy data, weather patterns, and grid electricity pricing. Moving on to the ETL and pre-processing pipeline, where we aggregate data from different sources, perform cleaning, normalization, feature engineering for temporal patterns. We also maintain a data lake throughout the process where we store different versions of our data, like the raw data, the clean data, which is used to train the baseline models, synthetic data for training the meta model, and analytics data for the dashboard and visualization. We train the individual baseline models, that is the LSTM, XGBoost, and LightGBM, over the historical data and create a synthetic data set, where each column in the synthetic data represents individual performance and individual predictions of these models, and the final column is the ground truth. We then train the meta model, which is a linear regressor over the synthetic data, which will be used for solar energy prediction. Now, this is the mathematics for the individual models. Now, moving on to the meta model. Now, a meta modeling approach strategically combines each base model's unique strengths, where the LSTM captures complex temporal dependencies, XGBoost models the nonlinear relationships, and LightGBM effectively processes high-dimensional feature spaces. So the goal of our meta model is to minimize the residual sum of squares by finding the optimal values of the coefficients. Here, H1, H2, and H3 represents the learned weights from the individual models. Now, the novelty in our approach is the dynamic pricing model which we propose, where we incentivize charging during peak solar generation periods while promoting grid stability and motivation for renewable energy utilization. Now, for meeting any user's energy requirements, this is the equation that we propose, where the total cost used to charge a vehicle is given by the integral of a combination of the grid energy and the solar energy and their respective prices, subject to the constraint that the energy requirement of a user is always met. Now, to take this with the help of an example, let us assume that 50 kilowatt is the battery capacity and we need 40 kilowatts to charge. Now, assuming that grid electricity costs 8 rupees per kilowatt, on a normal day where we do not rely on solar energy, we would save 0 rupees. And let's say on a gloomy day where we use a combination of solar plus grid, we can save up to rupees 75. And on a high solar generation day, we can save up to rupees 150. Now, the performance analysis is such that the dynamic pricing not only reduces the cost for users but also promotes environmental sustainability. Now, we can clearly see that the meta model achieves superior performance across all the metrics, that is the mean absolute error, mean squared error, and the highest R square value of 0.95. It also sees an improvement over the best individual performer, which is the XGBoost. This demonstrates the effectiveness of our ensemble approach. Now, this describes the box plot of absolute errors, which shows that LSTM has the widest error distribution with higher variability, And meta model is the most stable and has the most stable error profile with the narrowest interquartile range and the lowest median errors. Now, this is the hypothesis that we have, where we aim to define that the integration of meta model in our model building phase has no statistically significant improvement in accuracy, whereas conversely, the alternate hypothesis states that the integration of meta model into the system leads to a statistically significant improvement in the accuracy. Now, the threshold that we have kept is a 10% increase in accuracy. So hypothesis testing results. Now the t-test measures how many standard errors are observed different from the zero larger values, which indicates stronger evidence against the null hypothesis. Whereas the p-value, which is the probability of observing these results if the null hypothesis were true. Now we can clearly see that all the three comparisons exceed our 10% significant threshold and show extremely low p-values, allowing us to reject the null hypothesis in each of the individual cases. The most substantial improvement is seen against LSTM, which is 66.88%.
Hypothesis to test if the use of solar energy would provide more than 5% of cost savings as compared to using grid electricity alone. If we could prove statistically significant improvement, it would validate our cost optimization model. Optimization model, we simulated hourly energy usage data. The following data parameters were considered. So solar energy was modeled for both high and partial availability. The energy demand was specific to every vehicle and the costs were as follows: solar 2.48 rupees per kilowatt hour, grid rupees 6.25 kilowatt per hour, and the discounted version was 5 rupees per kilowatt hour. These are the two scenarios that arose when the solar energy was in excess as compared to the energy required. When the energy required was only 24.3 kilowatt hour and the solar was more, that is 42.16 kilowatt per hour. The outcome was that 100% of solar was used and there was no requirement of grid electricity. So the cost of solar came to 60 rupees whilst the grid cost came to 151 rupees. This led to a significant savings of 91 rupees, that is 60%. And the second scenario is the more difficult situation where the solar energy is in deficit as compared to the energy required. For this, we are partially depending on the solar energy while also depending on the grid electricity. So the combined costs was 150 rupees, whereas the grid only cost was around 300 rupees. This scenario also led to a savings of rupees 140, that is 49%. To test our hypothesis, we used a paired t-test between the grid-only costs and the hybrid solar grid costs. The p-value obtained was 0, which is far less than our threshold of 0.05. Therefore, we rejected the null hypothesis and confirmed that our hybrid model leads to significant user savings.
This is the demo of the dashboard which we have created for figuring out what will be the cost of charging the electric vehicle using the solar energy generated on a particular day using the API and the model which we have created. The dashboard takes the input as the vehicle type, which can be a two-wheeler, three-wheeler, or four-wheeler, and the solar center ID on using which we are charging the electric vehicle. The location is auto-detected, whereas the battery maximum wattage of a vehicle can be edited, and on the default it is taking the average value which is the default at the maximum wattage for a particular type, which is two-wheeler, three-wheeler, or four-wheeler. Charging budget is the amount which the user wants to spend for charging the particular vehicle. This is the final screen when the user gives the input for the particular parameters. The charging cost of 1 kilowatt is shown at the top, which is, let's say, at the particular time 8 rupees, and the comparison between the grid cost and the charging cost for solar. It also shares the details as to how much amount is being saved and the final result saying that charging using solar energy is profitable. Also, it shows whether the budget covers the full charging cost or not. Thank you for listening to our presentation and the details of our project. Thank you.